Welcome all. I am Mohamad Barbar, a PhD student with the University of Technology Sydney and CSIRO's Data 61, both in Australia. This work, Object Versioning for Flow-Sensitive Pointer Analysis, is a work with Yulei from the University of Technology Sydney and Chen from CSIRO's Data 61. To start, a quick overview of points to analysis. A points to analysis answers the question of which pointers point to which parts of memory. Memory is abstracted into abstract memory objects where each refers to one or more concrete or runtime objects. A points to set may look like this. We use points to analysis for a variety of purposes. For example, compile optimization, bug detection, and for instrumenting code with security checks. Generally, points to analysis enables other more specific analyses. Analysis precision depends on various sensitivities. For example, we must determine whether we should abstract fields into separate objects, whether to take control flow into account, which is what we are most interested in today, and whether we should consider calling context, amongst others. Generally speaking, a more precise analysis is more expensive in both space and time than a less precise one. Performant flow-sensitive points to analysis is staged and is performed on the sparse value flow graph, or SVFG, a diffuse graph. We first perform a fast auxiliary analysis, for example a flow-insensitive Anderson's analysis, where points to results are a superset of our desired flow-sensitive analysis. From there we can build the memory SSA form, which leads us to the SVFG, upon which we perform our flow-sensitive analysis. In the SVFG, nodes are instructions, and edges are divided into two types. Direct edges, which represent the value flow of named pointers, those which a programmer sees, in other words, top-level variables, and indirect edges, which represent the value flow of implicit memory objects, referred to as address-taken variables. The value flow of object O from node source to node dest means O is potentially defined at source and potentially used at dest. Here is what an SVFG may look like. This SVFG is actually a subgraph of a real SVFG modified a little for simplicity's sake. This SVFG has no direct edges and the edges indicate the value flow of a particular memory object O, so they are indirect edges. We stick to one object for simplicity of presentation, though our approach shines when many objects are involved. Instructions L1 and L2 are store instructions. Pointers Q and R, respectively, are stored in what P points to. In a points to analysis, this would mean that their points to sets are stored in the points to sets of the pointees of P. Instructions L3, L4, and L5 are load instructions. Pointers X, Y, and Z have their values set to what some pointers point to. We use an underscore here because for the example's sake, we are uninterested in what they actually are. Now, we can try to analyze this flow sensitively. We assume that over the course of the analysis, we have determined that pointer P points to object O, pointer Q points to object A, and pointer R points to object B. We are interested in the points to sets of O at various program points to illustrate our approach. The final such points to sets are shown in the first non-header row of the table on the right. The bar notation indicates where the points to set is. For example, this indicates the points to set of O immediately before instruction L2. We say that this points to set is in the inset of instruction L2. This indicates the points to set of O immediately after instruction L2. We say that this points to set is in the outset of instruction L2. To reach these results, we generate set constraints as in the final row of the table. When there is an indirect value flow between two instructions, from L to L prime, the points to set of O in the outset of L is propagated to the points to set of O in the inset of L prime. For example, since there is a value flow of O from L1 to L2, the points to set of O in the outset of L1 is included in the points to set of O in the inset of L2. Now we apply our approach. We version objects. An object version represents the state of an object. Per object, each instruction consumes a version, which represents the state of the object before the instruction, and yields a version, which represents the state of the object after the instruction. Instead of propagating from outset to inset, we propagate from the points to set of the version of the object yielded by an instruction to the points to set of the version of the object consumed by another. Since many instructions share versions across what they consume or yield, we reduce the number of points to sets required, as shown in the first non-header row, the final column, and the number of constraints generated, as shown directly below that, since many constraints end up being equivalent. Looking back to our example of the value flow of O from instruction L1 to instruction L2, our approach does not generate an equivalent constraint. The yielded version of O at L1 is kappa 1, and the consumed version of O at L2 is kappa 1, so they yield and consume the same version. A propagation would be useless since the union set operation is idempotent. Meld labeling is a pre-labeling extension which we will use to perform versioning. The result is that a node's label is a combination or melding of the labels of its incoming neighbors. Given a label domain K, we define a binary meld operator diamond taking in two labels and returning one. The meld operator is any operator upon K which is commutative, associative, idempotent, and the identity epsilon in K is defined with respect to the meld operator. Assuming kappa n is the label of node n, until a fixed point is reached, given an edge from n prime to n, where n prime has a non-identity label, we meld n prime's label into that of n's. Visually, this is the result of a meld labeling, where our label domain is a set of patterns, the meld operator combines patterns, and the blank pattern acts as the identity. On the left, we have a pre-labeling, and on the right, we have the final result. Node 4, for example, is a melding of the labels or patterns of node 1 and node 2. Importantly, nodes 4 and 7, and similarly nodes 5 and 8, have identical labels despite not sharing incoming neighbors, since the same set of patterns reach them. We wish to do away with the notion of maintaining points to sets at SVFG nodes or instructions, and instead maintain one or more global points to sets per object indexed by so-called versions. An object version represents a state of the object, such that two different points to sets of an object at different program points, of course, necessitate different versions. For example, version X of an object may be read at a set of instructions, and version Y may be read at another set. To encode the relation between instructions and object versions, we say that each instruction 1 consumes a version of O, represented by this C function, and 2 yields a version of O, represented by this Y function. The consumed version of O represents the state of O before the instruction, and the yielded version of O represents the state of O after the instruction. The result is that when versions are shared across instructions, points to sets are shared, reducing propagation and storage. This is an improvement in single object sparsity, whereby we improve sparsity on a per object basis, that is, each object can be represented flow sensitively with fewer points to sets. For versioning, we use meld labeling, where labels are analogous to versions and the pre-labeling to pre-versioning. For pre-versioning, we apply versions according to two main rules. Firstly, we cannot know before the analysis that a store instruction will modify an object's points to set. So we say that each such instruction yields a new version, or a preset version. Secondly, the SVFG is not static since on-the-fly call graph construction implies it is incomplete. At analysis time, what we term delta nodes may have new incoming edges as the call graph is constructed. We use the notation delta L as a function to show that L is a delta node. Since we don't know where objects flow from until analysis time and we want to perform versioning before then, we say delta nodes consume a new or preset version for objects of interest. Otherwise, at this stage, all other nodes would be given the identity version to yield and consume for each object. Overall, these rules give us a sound basis for versioning, but an imprecise one, since we lack analysis time information. We shall see in the evaluation that our versioning is still sufficient. Revisiting the earlier SVFG example, the pre-versioning would give L1 and L2 fresh versions to yield, since they are store instructions. The consumed version at these nodes would be the identity, and the consumed and yielded versions for O at other nodes would also be the identity. Now we can perform versioning. Each node or instruction may have two versions per object, one which is consumed or read, and one which is yielded or written. Hence, we introduce internal propagation and external propagation. Internal propagation is a propagation of versions within a node, from the consumed version of an object of a node to the yielded version of that object in that same node. When we have non-store instructions, instructions yield what they consume since they do not modify object points to sets. On the other hand, store instructions had their yielded version set earlier in the pre-versioning phase and so can be left alone. The inference rule on the left encodes this. External propagation, on the other hand, is between nodes along indirect edges, or value flow, from the yielded version of an object of one node to the consumed version of an object at another node. The consumed version of an object at non-delta nodes, which had their consumed version set earlier in the pre-versioning phase, is a melding of the yielded versions of the object at incoming neighbor nodes. This is encoded in the inference rule on the right, where given a value flow of O from L to L prime, the consumed version of O at L prime is a melding of itself and the yielded version of O at L. Revisiting our example, after the versioning phase, this is the result. Instructions L2 and L3 have their consumed version of O set to kappa 1, propagated from the yield of L1. The consumed version of O at L5 and L4 are a melding of kappa 1 and kappa 2, propagated from L1 and L2. And the yielded versions of load instructions L3, L4, and L5 are what they consume, since the instructions do not modify them. Now we can modify our analysis to use versions instead of in and out sets. We focus on the most important parts. For a load instruction p equals star q, in the pointer set of p, we include the pointer sets of the pointees of q, each object O. Before we would receive these pointer sets from the inset of the instruction. Instead, we now retrieve the consumed version of O and use the pointer set corresponding to that instead, which may be consumed or yielded by many other instructions. Similarly with store instructions. Given star p equals q, typically we would include the pointer set of q into the pointer sets of the pointees of p, each object O, in the outset of the instruction. Now, instead we retrieve the yielded version of each pointee O of p and include the pointer set of q in the pointer set of O corresponding to the yielded version, which again may be consumed and yielded at many instructions. Another difference is how propagation of object pointer sets between instructions, that is, along indirect edges or value flow, occurs. Typically, when we have a value flow of O from L prime to L, we would include the pointer set of O in the outset of L prime, in the pointer set of O in the inset of L. Now, we can use the yielded version of L prime and the consumed version of L instead, using the pointer set of O corresponding to each of those. For multiple L prime and L, we may have the same kappa S and kappa D, leading to reduced propagation and reduced storage. We have implemented our analysis in open source points to analysis framework SVF. We compiled some benchmark programs, shown here, using the whole program LVM project and Clang 10 and analyzed the resulting LVM bitcode with our analysis and a baseline flow-sensitive points to analysis already available in SVF. Of these programs, Ninja, A-Style, and High-Rise Console are written in C++, and the rest are written in C. There is no easy to discern correlation between any of these stats, and analysis time and memory usage, like top-level variable count or lines of code, as we will soon see. We gave SVF a maximum of 120 gigabytes to analyze each of these programs, and a maximum of 12 hours to analyze each of these programs. No analysis exhausted the time limit, however. First, we look at analysis time. The Anderson's column shows the time taken for a flow insensitive analysis, which is actually what we built the memory SSA form and the SVFG from. The times are generally much lower than the main phase of any flow-sensitive analysis. The SFS column shows the main phase time of the baseline analysis we are comparing to. It excludes the auxiliary analysis time and the time to construct the memory SSA form and the SVFG. In analyzing one program, links, the analysis ran out of memory. Then, in this VSFS column, we have the time taken for our analysis, a sum of the versioning and the main phase time. Finally, the time difference column shows how many times faster our analysis is. The geometric mean speedup is 5.31 times. For some benchmarks, we see a drastic speedup of more than 10 times. For two of our benchmarks, however, we see a much more modest speedup, around 1.5 times only, which is still acceptable, especially considering that D package could be analyzed very quickly already. Generally speaking, versioning makes up a small portion of analysis time, except in smaller benchmarks where the main phase is very fast. Some slower to analyze benchmarks, however, do see around 10% or more of the time taken in versioning. We believe our versioning implementation can be sped up, but returns will obviously be very little in the grand scheme of things, considering the general difference in versioning time and main phase time. There is still room to improve the implementation of our main phase. For memory usage, we show the maximum resident set size. First, for a flow insensitive analysis, no program took more than 3 GB to analyze. Then, for the baseline flow sensitive analysis, memory usage starts to become a problem. In analyzing links, the 120 GB limit was exceeded. In our analysis, no benchmark required more than 22 GB to analyze. The final column shows the memory reduction our analysis presents, giving us a geometric mean of 2.1 times or more. For a few larger benchmarks, we see drastic memory usage reductions, but smaller ones do not see the same success. The space required for versioning grows much slower than that required for the main phase, and performing the main phase with versions helps reduce memory usage. So for benchmarks with a smaller main phase, versioning starts to take a larger proportion of overall memory usage. In all, we have described object versioning for flow-sensitive points-to analysis, where the points-to sets of objects can be better shared at multiple instructions through improved single-object sparsity. We see an average speedup of over 5 times and around half the memory usage in our evaluation than by storing points-to sets for each object at each interested instruction. Our implementation has been merged into mainline SVF, and instructions on how to use it are available at github.com/svf-tools/svf/wiki/vsfs. Thank you.